Okay, so we're back with class number 9. This is video 2. I probably talked too long in video 1. Oh well. Because I wanted to also include in types of pressure, I also wanted to talk about within Bernoulli, there's also some types of pressure that we want to think with some of the combination, right? So we already talked about the static pressure, the dynamic pressure, and the hydrostatic pressure. Well, together, the static pressure and the dynamic pressure, they form the stagnation pressure, right? So I described the pitot tube in the first part of this right here. So here's our pitot tube describing this. The pitot tube stops the flow right here at this spot. So it really grabs these two guys together and makes them into a single pressure that could be felt by maybe a transducer, or it could be, we can maybe use a manometer here, combined with the static pressure. So there's these little tiny holes on the side, and they get to be measured right here. So the difference between we could measure the difference between these two, and that will be the difference will be the dynamic pressure, right? So we're able between these two things to figure this out. Like we'll be able to isolate. That's what I want to say. We're going to isolate the dynamic pressure, and therefore we could figure out what the velocity is going to be. And with that velocity, we would be able to figure out what the flow rate is going to be, because we have the velocity. We can take the area. We can assume maybe it's going to be this constant across the cross section right there. So if we have a pitot tube inside a pipe, we're able to find what the flow is. We can also isolate the velocity and find what the aircraft speed is going to be. And these have pitot tubes. Sometimes they'll have several redundant ones. Sometimes they'll be heated too, because they might ice up. Because we have these itty bitty little holes right here. They're kind of dangerous, right? So this is these pitot tubes. If you are often used to judge airspeed, and if you and that might be instrumented into a control circuit, and if the control circuit gets the wrong airspeed, it might cause problems. Let's just say that with an aircraft in the control system. But this can also be used, by the way, as I mentioned, as a means of measuring flow. So it's got two real big time uses, and that's maybe get the airspeed in aircraft, but also flow inside inside any vessel where there's fluid flow. We can also say the total pressure is something that's going to be all of these things combined. So I think I've beat that into the ground. So let me do an example. Now that I've stammered a lot. Here's slides from Single, just repeating some of the same things that we've just said. All right, so here's my example where I have a Venturi. It's a constriction in the pipe, where we go from a diameter for 2.5 inches to a diameter of 1 inch, and we want to try to find out what the pressure is going to be at that location labeled as 2. Now, all we know at this point, we know that this is going to be 10 feet per second coming in here at 1, and we want to find out what the pressure is at 2. So we know the velocity at 1, and we know the pressure at 1, and now we want to know the pressure at 2. So let's change this thing over. Okay. So one of the first things I want to know is what the velocity at 2 has to be, right? Because let me write down my main equation here. 1/2 rho v1 squared plus gamma z1 is going to be equal to p2 plus 1/2 rho v2 squared plus gamma z2. Well, this is there's nothing that says it was going upwards, so these two will cancel out. They're at the same height. But we have P1. They tell us it's going to be 20 psig. We're going to stay with gauge pressure. So let's stay with gauge pressure and say that it's going to be 20. But I'm going to work in feet pounds per square foot. So I'm going to multiply that by 144 inches squared per foot squared. And then I'm going to go for my 1/2 times my density. I'm going to use this is water, which is 1.94 slugs per cubic foot. And we're going to go times 10 feet per second squared. And that will get us into pounds per square foot. We're going to equal what we want to know here, and then plus 1/2, 1.94. Oop, we're stuck. We don't know what V2 is going to be. So we have two unknowns. We have the velocity and we have the unknown pressure. So we need something else before we continue. So we'll leave a little blank spot so we can finish up our work here and come down here. But what else we know is that the mass flow here, m dot 1, has to be the same as the mass flow here, m dot 2. So m dot 1 must equal m dot 2. And another way of writing that is density times volumetric flow 1 must equal density. We can call that 1 and 2 if we want to for right now. But, so this is definitely this is conservation of mass, has to be true. Just nature says that has to be true. But here we can say, these have to be equal to each other if incompressible, which is good news because that's also one of the conditions that we have to have for Bernoulli to work out. And water is very incompressible. It could be compressed every so slightly, but it takes a whole lot. So just treat it as incompressible. We can also say the volumetric flow rate can be broken down to velocity times area. So the velocity times the area equals the flow rate. So 1, 2, 2. And then, of course, lastly, we could say that the, I guess I'm flipping around, pi d1 squared times velocity 1 is equal to, I'm running on a page, pi over 4 d2 squared v2. Of course, the pi over 4 cancel each other out. So for our velocities, we could flip this around and say velocity 2 is going to be equal to diameter 1 squared divided by diameter 2 squared times velocity 1. Did I do that right? I think so. So this went from 2.5 inches to 1 inch. We don't have to do a conversion because we're just taking we're using inches, right? So we're just taking a ratio right here so that all the conversions would have canceled out. And we have our 10 feet per second. And this comes out to 62.5 feet per second. And now we know this. So we could come back up to here. That's our unknown, 62.5. And we can find our P2. It's going to be a negative number. Turns out to be a negative number. 812.1 pounds per square foot. Now that doesn't, maybe that could be the answer. But I think I would rather, turn it into PSI. So divide it by 144. And you get negative 5.639. Remember, that's PSI G, right? So this is referencing with having 0 as being atmosphere pressure. So this is negative. Typically what we will do, though, is we'll actually, for most gauges, pressure gauges, that could possibly be used for that where vacuum is possible, they'll have this as being 0, and they'll label this as PSIG, or they'll label it PSIG up along here, but in this direction right here, they'll go inches of mercury vacuum, right? So they'll have, it'll be a positive number as instead of having a negative number. So that's just what's typically done. The easiest way for me to do this is to let's look at this. This is the amount of vacuum. Let's see. I have a student waiting, so I have to finish this up. 800. I'll take 812.1 pounds per square foot, and I'll divide it by the specific weight of mercury, 847 pounds per cubic foot, which ends up going 0.9588. And what this ends up being is feet of mercury, but vacuum. Well, most of the time we use inches, so we just multiply that, and what we will have is 11.51 inches of mercury vacuum. And that would be a more standard way of reporting what's taking place in this Venturi tube. So I have to exit now, but that's one more video down. I got one more to go for class 9.